Ilnytskyi from the Ukrainian Academy of Sciences, and he will talk about microphase separation-driven transitions in macromolecular liquid crystals by computer simulation.
Thank you very much. Is it working? Is it working? Yeah. Okay, so first of all, I would like to express my thanks to the organizers for inviting to present our results here. And the talk was just announced, and I came from the Institute for Condensed Matter Physics from Ukraine. So here during the workshop, we saw several times complex polyphilic systems when the molecule is consisting of several incompatible groups. Say there could be incompatible chemically, in size, in shape, in their flexibility and stiffness. And similar groups stick together by means of also several mechanisms. This could be static effect, packing, depletion forces explained in one of the talks yesterday, attraction forces. And also we have a competition of enthalpic and entropic contributions when such things try to self-assembly, say into micelles or in some ordered phases. And I would like to concentrate in my talk on two cases, and basically they are united by the fact that both systems are macromolecular and both are polyphilic and containing liquid crystalline groups. And the things which are important for our work is self-assembly, or in our case it's more aided self-assembly, how it is performed, how we can steer the system into a self-assembled state, and also the stability of the phase after formation. So the first part is a simulation of smectic liquid crystalline elastomer, and I will just say a few words about liquid crystal elastomers. It is well known they combine both polymeric matrix and liquid crystalline subsystem. Mechanical properties are most exclusively defined by the properties of the polymer network, with some exceptions. Say this is just cosmetics. And a reaction on external stimuli, such as electrical field or say chemical conditions or the light, is mainly due to the part of liquid crystalline groups. And sometimes it is called that system can split into two types with positive and negative coupling between nematic or the nematic director and the axis of the uniaxial extension. So that means that if we stretch during some axis, then the liquid crystalline director is oriented either parallel or perpendicularly to the axis of the stretch. The main applications are some based on the reversible shape changes under external stimuli. So, for instance, if we have some ordered phase and we can heat the system up, or we can illuminate if the elastomer contains some photosensitive groups like azobenzene or other groups, and the shape changes reflecting the changes in the liquid crystal system, then due to coupling it transformed into the shape of the system. But when we remove the external perturbation, then the system reversibly returns to the previous state. And vice versa, if we affect mechanically the backbones or say polymer matrix in general, then also we can see some transitions like stress-induced destruction of the liquid crystalline order, or stress-induced induction of the liquid crystalline order. And again, when the stress is removed, we get back to the original state. Here, I can use this. Right, so what are the main, so typically SMECTIC elastomers are built up of sidechain architecture with a relatively long spacer, 6-12 monomers. It is similar to the previous talk when the, say, SMECTIC phases were known to be observed when we have quite long hydrocarbon chain attached. And also the main differences from pneumatic liquid crystalline elastomers is that a pneumatic elastomer is isotropic mechanically but anisotropic optically, while the SMECTIC elastomer is anisotropic both mechanically and optically. And we have well-defined lamellar morphology with alternating layers of liquid crystalline groups and polymer matrix. And so mechanically it behaves like one-dimensional solid in this direction and as elastic two-dimensional network in this direction. So it is reflected in high anisotropy of Young modulus, around say 70. And the reaction of the system is very different while stretching in this or that direction. Okay, modeling. So what we would like to achieve with our modeling. A huge deal is known theoretically about such systems. And also since late 80s, we know a lot from the experimental study. So what new could provide modeling? It is quite difficult question. And I would say that our task was quite modest. We were sticking just to idea to reproduce the main features of what we can see on the experiment. So later, if say the approach works, then we can easily change the molecular topology and try to say to play with the parameters and to look for some things that could be predicted. So far in this talk, I am not predicting anything, just trying to reproduce the main features of the liquid crystal elastomers in the SMECTIC phase. So there are a number of previous simulations outlisted here using different approaches, including lattice model. Of lattice models, many of authors are in the audience. And what kind of modeling issues we are facing in liquid crystal elastomers? That first of all is the size of the system. So why the system should be of the large size? So this is the network of the polymer network, and to have the entropic elasticity of the network we have quite we need large conformational space of the chains between the crosslinks. So this already means that the chains should be sufficiently long. Also, we need very weak, weakly crosslink system. Otherwise, we will end up with the thermoset and other solid materials. So that means that chains should be long and the crosslinks should be not so many. So that blows up the required size of the system. So locally also it is viscous fluid here, and this means that relaxation times are high. And say the best would be to have several samples and to average the properties, or say the huge sample to exploit the self-averaging property by the size of the sample. However, in our model, we just tried minimalistic approach. So we tried to use some moderately sized system, and it is built up of the molecules that are outlined here. The backbone is made from 100 molecules, and we have 50 side chains. 40 of them are terminated by mesogenic groups in the form of gay Bern particles that were also discussed in several talks already. We used united atom approach for the polymer system. Again, the previous talk addressed this type of modeling. We do not have any electrostatics, and say what we have is again the polyphilic system where the parts are not mixed very well because of the shape and because of the difference in the interaction potential. So when it is known from the experiment when the spacer is quite long, then we have nicely microphase separated smectic phase, which we basically obtained here, aiding by external field which aligned the mesogens along one direction. But then the field was removed and the system was relaxed during 20 nanoseconds. So here is just to show the backbones, and we see here some defect of our structure where two chains are merging basically two layers. So typical dimension, so we have 28 of such molecules in our melt. So so far this is melt, this is not elastomer. Typical dimension 150 angstroms, and simulation times we had around 100 nanoseconds. For the large system, we can allow the system to cross-link between the thread chemically active sites completely randomly. But for the small system, of course, we may end up with some very inhomogeneous cross-linking of the system. So that's why we tried to do this in a controlled way. And so first we map all the distances between such chemically active pairs and place them into the list and sorted that the closest pairs are on the top. Then we split the system into cuboidal domains and loop over domains looking for the pairs which are located in the list. And so far we did this loop as many times as needed to perform cross-linking with the number of links which we desire. So in our case, number of cross-link is equal to the number of molecules. And ideally, we would like to have the single network topology, but unfortunately, when we end up with some large network and several smaller subnetworks. And I must say, unfortunately, this idea to analyze how the topology came to the authors later when all the simulations were performed. So we basically cannot get back and recalculate this. But if possibly we would be trying several times, then we possibly may end up with the single network topology. Okay, I need some formulas, otherwise it's more only the snapshots. And if we have such anisotropic system and we study anisotropic deformation of elastomer, we need the proper ensemble, which in our case is anisotropic isobaric ensemble. And one can see this as simplified version of Parinello-Raman ensemble, where only diagonal components of stress are constrained. And so one can obtain it from the scaled Lagrangian and then obtain a Lagrangian equation of motion. And so it basically splits the conservation of the pressure into three components alpha. And otherwise, in terms of thermostating, it is uniform. It is the usual thermostat in the form of Noether-Hoover. Okay, so now I would like to address this experimental studies that we are trying to reproduce. So first is that it is well known that cross-linking stabilizes the phase in which the melt was cross-linked. So it is reflected in the fact that the nematic isotropic transition is shifting upwards. So if we we cross-linked the system in the ordered phase, it became more stable due to memorizing the positions of the chains at the stage of the cross-linking. And typical jump of the transition temperature is, say, 710 degrees. And actually, this is what we checked the first. So here, we started from the system deep in the smectic phase at 450 Kelvin here, and one can see that the order parameter is stable here. Then we gradually heated this system to higher temperatures, and the transition took place somewhere between 500 Kelvin and 505 Kelvin for the non-cross-linked system, for the melt, and about 5 degrees higher for the cross-linked elastomer. So we can see that at 505 the system still retains the orientational order. And also synchronously with this we see the deformation of the system along the nematic director. So we can see that also the system keeps its shape. So this is first indication of the coupling between the order and the mechanical properties of the system. So we are quite happy with this result. It is in the reasonable range, and also, as I mentioned, here is a synchronous change in the order parameter and in the deformation. Now the main thing is the memory effects for such systems, and experimentally it is known that the heating and cooling cycles provide reversibility in the strain of the sample, and also it could be mapped to the strain and order parameter of the sample. So we can see again remarkable synchronicity in both, which reflect the coupling. And we would like to reproduce this in our simulation. And again, what we did is that the sample at 450 Kelvin was heated above the transition to 510 degrees, but then several reverse cooling cycles was done. So after the sample was held at this high temperature only for 4 nanoseconds, 12 nanoseconds, 20, and 28 nanoseconds. And what we see basically is that for the liquid crystalline melt, the shape of the sample here is lost after the system was held above the transition more than for 12 nanoseconds. But for the elastomer case, we see that the shape nicely returns to the original strain of 1 when we cool the system down. So basically, here only when we held the system very short time of 4 nanoseconds, we have the retention of the order. And here we say the time window of our reversibility for our model elastomer is 40 nanoseconds. Here are some snapshots how all this looks like. So here is the original system, which is similar in both cases, but here we have the cross-links here in blue. And we see that after the system is held for 28 nanoseconds, here the backbones positions are lost, and upon cooling the system, it doesn't return to the original state. And while for this case, there is obviously some diffusion, but the cross-links are memorizing the original position of the backbones, and we see that upon cooling down after 28 nanoseconds, we return absolutely the same structure for the elastomer. So we reproduce this reversible effect. Here one can see that the origin is possibly diffusion driven, and we checked this by calculating the mean square displacement of the polymer sites along this axis, and here we can see that the diffusion coefficient for the liquid crystalline elastomer is approximately 2.5 times lower than for the melt. So basically crosslinks are blocking diffusion of the chains, which is obvious thing. And also here we can see that there is some typical distance to destroy the lamellar, and basically this distance is here kept very well. So the cross section of this linear fit of the mean square displacement with some maximum value for it, which is just square of this distance, indeed say here is something like 12 nanoseconds, here is 35. So we are quite confident then destruction of the order here and keeping the order here is just based on the reduced diffusion. Okay, now what happens when we apply the mechanical load? When we apply the mechanical load, smectic reacts very differently, as we know from the experiments more than 10 years ago. So if we stretch the elastomer in this direction, we effectively are stretching only two-dimensional polymeric network. And nothing happens with the smectic layers in the perpendicular direction. And this is reflected in this picture taken from that papers above, that here the width of the sample doesn't change, and also the order also doesn't change because the sample is still transparent. And the strain in this direction could be as large as 200%. So we did the similar simulation with our model, and here we see that the backbones are getting anisotropic due to the uniaxial stress being applied, so the ratio is about 4 of a parallel and a perpendicular component of the radius of gyration. But the deformation of the system, a strain of the system in this direction particularly is absolutely stable, as well as all the order. So the order along each axis is also stable. So that means that our network sustains this applied uniaxial deformation, and we can reproduce these experimental things. Now again about if we stretch the smectic elastomer in this direction, we have quite opposite situation. Here the sample shrinks and it became turbid. So it was suggested in that papers that smectic layers undulation is taking place here, and that's why we have non-transparent sample. So what we did, we just made applied a constant stress, uniaxial stress, and we indeed have some two regions, two typical regions for the elastomer. In the case of the melt, the sample is kept for some time and then is destroyed. But for the case of the elastomer, we have this nice elastic regime where it withstands the pressure after this flat region. And one can estimate the anisotropy of the Young modulus here, comparing this to strains at the fixed stress, and we have something like 60, which is also comparable. And on the snapshots, it looks like the following. So first, the behavior of the backbones anisotropy. Here we again see that backbones anisotropy, the numbers are here for this black plot, is sharply increased. and also the order is switched. So the order parameter was originally high for z axis in this direction, but if we stretch in this direction, at approximately 10 nanoseconds, we have the uniform reorientation of the director, which can be seen on this snapshots. Say for another sample, which is different by a thermal history. So here we have a cross-linked sample, which was well equilibrated at 450 Kelvin and then heated up to 480. But here we have the cross-linked sample, which was heated first to 500 degrees and then cooled down to 480. And we have such a chevron structure, or in our case, it is just only one, so it is a V-like structure here, and the sample eventually breaks. The explanation of this is well known from theoretical studies and is outlined in these papers. So the bulk modulus is very anisotropic, and the system doesn't want to be extended in this direction. Instead of this, the shear modulus is much smaller, so the system is looking for the opportunity to share. And basically here we see that our volume element, which represents the piece of the elastomer, is uniformly rotating, and here it is split into the two subdomains, which both rotate but in the opposite direction. Our interpretation is similar to the nematic elastomers here. So it is known that if one stretches them at some oblique angle, then one observes the uniform reorientation of the director. And here what we see is that the angles in both subdomains are different. So they start to rotate separately and split eventually to break the system. So that's our results and conclusion to the part one. So in fact, we had very small system size, but attempted to cross-link it quite uniformly, and observed a number of experimentally studied effects, that stabilization of the smectic phase if the system was cross-linked in it, and also memory effects in liquid crystalline order and strain when we drive the system through the smectic isotropic transition, and a typical reaction of the system on external uniaxial stress. Let me come to the second part, which is somehow similar in the approach and in our simulational technique, but it is about bulk self-assembly of the polyphilic macromolecular crystals. So here is some known, excuse me. Here we have some known facts from the experimental studies and some excellent reviews about the polyphilic liquid crystal supermolecules. So basically, despite different chemical constitution of such macromolecules, one can generalize them that they have some core, which could be organic or inorganic, say a gold nanoparticle or something else. Then some organic spacers made of hydrocarbons, and a mesogenic surface. So basically, the factors that influence the phase diagram of such system are several. First, this is the density of the external mesogenic surface. So if we have very low density, then the system tries to build into the lamellar phase. If one increases the density of the external shell, we have columnar phases. And for very high density, we have cubic phases. So the objects are similar to the compact colloids. Another factor, of course, is the temperature, because the entropy, conformational entropy, will always try to make the thing spherical, and at high temperature, of course, it finally achieves this, and the system could form cubic phases. But if the temperature is lower, then competing mesogene interactions are basically a competition between two tendencies, result in formation of either lamellar smectic or say a rectangular columnar phase or hexagonal columnar phase, which was known from the study made in 2000. Also, it depends on the generation of the dendrimer. So here the dendrimer is basically this core. And this picture is only valid for a sufficiently large generation of the dendrimer. Quite similar phase diagram and dependence on the temperature and on the density of the external layers are also found in the gold nanoparticles, which is coated by chains terminated with liquid crystalline groups. So here is some recent review about these particles, and what kind of modeling we can do to simulate, to try to study self-assembly of some particles. Of course, we cannot do atomistic simulations, unfortunately, as in the previous study. The number of molecules should be quite sufficient, and also each molecule is macromolecule, so it is a supramolecular chemistry plus supermolecular chemistry, so this is too much. So here we just decided to use some generic coarse-grained model, which has the central large bit, a spherical bit, and then there are certain number of chains attached to it, and each chain is terminated by a mesogene. And what kind of relation this model has to real systems? So one can point out several cases. For instance, if we have gold nanoparticles which are covered by the polymer chains, then one would think about pinning the chains to the surface in certain places by covalent bonding. Say for the liquid crystal dendrimer, here the core is flexible, and each chain is can be seen as attached by some spring, and we can introduce some angle here, which some harmonic term which adjusts the flexibility and the possibility for the chains to move on the surface. But of course, it is nice to study from the most simple model, and this model is just freely sliding chains. So they are not attached in some particular places, but only by the springs which define their bond length to the center of the particle. But otherwise, they are free sliding on the surface. So we started from this model, and say coarse graining was mainly done in this paper, not by me, by group of Mark Wilson. And you say the central sphere could represent a generation 3 dendrimer or a gold nanoparticle. Then we also coarse grained several groups into one sphere, say 3 hydrocarbons into one blob. And also the mesogenes are represented like in the form of spherocylinders. The potentials that we use are outlined here. For the spheres and mixed interaction, we just use very simple quadratic potential, which is typical for the dissipative particle dynamics simulations. And so it is a soft repulsion here. And for a spherocylinder, we used the potential suggested by Lintuvori and Mark Wilson, and also it was in several talks already yesterday and 2 days ago. So the main feature of this potential is that on the top of this soft repulsion between the spherocylindrical cores, we have some attraction in some distant range of distances which make the shallow well. And the main purpose is to stabilize the side-side interaction to induce mesogenic behavior at smaller L to D ratio. Otherwise, one should take extremely long rods for entirely a soft repulsive model to have any liquid crystalline phases. And this basically model, as I said, was used already in many papers. So just very naive approach here to what can we achieve just by purely packing analysis. So here we have the say our model, and one can imagine several structures that can made out of it depending on the number of the chains. Say if number of chains is not very large, then we can think about rod-like structure. When we increase the number of chains, we can think about disks, and again, for very large number of chains, we can see the three-dimensional spherical particles. Can we just estimate how many chains we can fit into this free volume, and then maybe to aid our computer simulation of the phase diagram? So first we assume that there is interdigitation of our mesogens, and we know again from the previous talk that the chemical nature of this is pi-pi interaction between two aromatic groups that are in oppositely pointing mesogens. So we can just think about some cylinder and subtract here the spherical particle and calculate how many chains we can get here inside if they can closely pack. So it's something like 29 for our dimensions. Then for the disk-like particle, we can theoretically pack here 170 particles, quite a lot. Also, we assume interdigitation here. And for spherical particles, it is something like 245. But the things that were mentioned by the author of this paper is that not all the available volume can be packed efficiently because we have the radially pointing chains. So basically, the number of chains will be limited by the available area of the sphere. So we can calculate that, say, if they are touching, that only 46 are able to place tightly on the sphere. So all this basically doesn't work because we have inhomogeneous density for such objects. So this analysis is not so accurate, I would say. And we just try simulations. So we considered the cases of 8, 32, and 48 chains here. And we, to aid the self-assembly of the system, we tried to induce certain shape by the external field which get the required symmetry. So that means that if we would like to induce the rod-like shape, then we applied the external uniaxial field which aligns only the mesogens, and we will think that the molecules will adopt this shape. And also if we apply the planar field with which will prefer the mesogens to be perpendicular to some axis, then we are going to reproduce the disk-like shape of this molecule. This basically works nicely, say, and for the system with 8 only chains, so a small number of chains, if we start from the disordered phase, we have very nice asymmetric self-assembled layer. But if we induce the planar field, then still we get the symmetric layer because we have a insufficient number of chains to make the disk. So basically the symmetry of the field is such that it promotes the mesogens to be perpendicular. And yes, they are perpendicular, but here in this plane, the two-dimensional symmetry of the rotation is broken, and we have still here uniaxial symmetric layer, absolutely similar to this, but placed in the different in a different way. If we cut the layers here, then we can see that they are almost closely packed, but not so for the mesogens, where we have a big voids. And also this was mentioned in the review on nanoparticle by John Goodby and co-authors. So it's not always that you can pack tightly all the components. And here what is interesting that we can see some percolation paths. So basically the layer will be stable if we have the percolation of these joints between the mesogens. And one could suggest that if there is no percolation, then the system splits into the polydomain phase. So what happens if we increase the number of chains, say, to 16? Whether these voids are filled? No, they are not filled. And we can see that the system is not packed as tightly as for the previous case. So what happened that basically entropy, conformational entropy is driving the shape from the rod to more expanded rod. So there is more distance here to fill some mesogens, and again, it is not enough mesogens. And absolutely the same is for the 32. So we have some delicate balance here between the entropy, which tries to make the things spherical, and the enthalpy of attraction between the mesogens here. So always we have some voids. And so if there are more chains, then still entropy is driving the shape to swell. Right, let me consider here now the opposite side, the opposite case of high surface density. So here I have 48 chains, so much more than before, and the situation is quite opposite here now. So if I apply a uniaxial field, yes, I can get something which is caricature of the lamellar phase, but it is unstable, and it after the field is removed, it is just turning into the cubic phase. But if I applied the planar field, then I get absolutely perfect columnar phase, which can be seen from this from the side. So it is absolutely a perfect correlation between the disks in this direction, and we see very nice, in fact, ideal structure for the disks. Now, if I heat the system up for this case at higher temperature, what I have is cubic phases. And 2 cubic phases are achieved depending again of the thermal history of the sample. If I have a system which did not have very, with no field applied, then I end up with the cubic system which has hexagonal packing on each side if I turn around the simulation box. But if I heated up this system, then we can see that the structure of this phase is different, because here I have rectangular packing, and here is hexagonal packing. And it is very difficult to say whether this is a really cubic phase or some deformed a columnar phase, because there is, as I understand, maybe I understand something incorrectly, there is no sharp transition between the disk and, say, deformed disk and the sphere. So we didn't analyze the structure here, but we are planning to do this in some rigorous ways. Okay, and the question is that for low density of the chains, we have a lamellar phase. For high density of the chains, we have a columnar phase. And can we achieve both phases for certain number of chains? So whether we can have the dendrimer, which is a kind of shape switching, depending on the external field or another environment, we have either rod or disk. That would be a really nice, interesting thing. And it turned to be that for the number of chains 32, this switcher indeed exists, and this is the symmetry of our field. So if we applied uniaxial field, we have stable, after the field is removed, of course, stable symmetric phase. And if we apply the planar field, then we have stable columnar phase. And here typical shapes of the molecules are shown here on the top of the snapshots. So basically for this value, we have a very nice ability of this, our generic model, which represents either a dendrimer or a gold nanoparticle covered by liquid crystalline chains, to change the shape. And here I would like just to show some radial distribution functions, and also say evaluated for the lamellar phase within the layers. And we thought maybe here we have some hexagonal packing, but it is rather not well defined, I would say. And here in that direction we have very clear indication of the layers. We also calculated symmetric order parameter, which was of the order of 0.7 here. And the interesting question for us, and I believe just in general, was how the symmetry of the phase is related to the asphericity. So whether all these changes, so when I heat up this phase, whether the change of the shape of the molecule is coherent with the change of the phase. And what we have here is symmetric, nematic order parameter going to 0 at 500 degrees. And also the same is the asphericity of the molecules, absolutely following the same route, where asphericity is evaluated as some combination of the components of gyration tensor. So we have absolutely perfect correlation between the shape of the molecule and the phase. And that was also suggested in the experiments about this strong correlation between the shape and the symmetry of the phase. And the same about the columnar phase. Also here, the order parameter along that axis is negative because they are perpendicular. So we have absolutely the same temperature where it turns into the isotropic phase. And this is another question. So both phases disappear at the same transition temperature of about 490, 500 degrees. So that means that these locks provided by symmetric ordering, they are responsible for destruction of this phase. So since here the liquid crystalline subsystem is having the order-disorder transition, after this the system splits and there is no ordered phase. So basically, to summarize this second part again, of course, as one could understand that this opens up future continuation of this work, that we can change the topology of the chains, or we can study polydispersity of the chains. Also, we can pin the chains to the surface and trying to predict what the new phases or how the phase diagram is changing due to these changes in the molecular architecture. So we would like to build complete phase diagram. Also, we are currently studying self-assembly in pores with different anchoring scenarios and study some other cases. And I would like to thank all people with whom I collaborated. They are here. And also, funding was via IDF GAG grants, EPSRC, and European 7 Frame grant. And thank you very much for your attention.
Other questions? Yes.
You, the first part of your talk, when you deform the materials and apply stress, what kind of stress was it? Was it uniaxial or biaxial?
Yes, it was uniaxial stress, but actually what we did, we applied uniaxial stress here in one direction and then two opposite stresses in other directions, trying to conserve the volume of the system. Yeah.
Constant volume.
Yeah.
Any other questions? A lot of the features of elastomers are on a length scale longer than what you're able to probe. Do you envision any way of getting some information about longer length scales?
Well, first of all, if the small system works, then the same model for the larger system should work, but we can save a lot of time just checking on the very small system, which is obvious thing to try. Also, what I learned from the literature is that for the large system is more homogeneous because it self-averages over all these defects like dangling fragments and say a non-uniform distribution of the crosslinks. And if we cut from the material the small size, of course, there will be a lot of these defects. So that's why we tried to minimize them by controlling the cross-linking. So we feel that in this way we somehow map the larger system. But of course one needs just to make a larger system here.
Very good. So, one.
With the pneumatic elastomers, could you get something like a monodomain, polydomain to monodomain transition when you apply stress, or is it too?
We didn't study pneumatic elastomer.
The pneumatic, I mean.
Yes, but for smectic elastomer, I can show this slide here. Originally, sample was isotropic, and if we stretched it, we have induced the order in the perpendicular direction because we have a negative coupling of it. So basically, what we have here is a stretched system with some order in y direction of the order 0.4. That's what we got. But of course, the elongation is huge for the system. So that means that a system should be made larger. And
Yeah, that's what.
Yeah.
For the pneumatic phase to see what.
Well, yes, for pneumatic phase, one need to modify the model, say to have the polydisperse spacer lengths to suppress smectic layers, as I understand.
Okay, there are no more questions. Let's thank the speaker.